the structures around you, you will observe that the world is full of geometrical shapes. Look at these bridges, railway tracks, and these modern buildings. They all are applications of geometry. But these applications of geometry are not manifestations of the modern world. Since time immemorial, human beings have been constantly utilizing the principles of geometry to make their surroundings comfortable and beautiful. The Rome Colosseum is the finest wonder to prove that geometry was utilized in the ancient times too. Geometry was used primarily as a means of measuring and calculating the distances. Let's study the development of geometry till Euclid's time. Major early development of geometry occurred in Egypt, Greece, Mesopotamia, and India. However, the major evidence of earliest development of geometry can be seen in Egypt. The Egyptian pyramid is an epitome of use of geometry. The principles of geometry were also applied by the early Babylonians in Mesopotamia. They displayed their knowledge of geometry by giving accurate formulae for calculating areas and volumes of simple geometrical shapes. Development of geometry can also be traced in the Indian subcontinent during the ancient Indus Valley civilization. The highly developed and planned cities in this civilization, known as Harappa and Mohenjo-daro, display the application of geometry in various spheres. These cities had parallel roads, and the houses had rooms of different shapes and sizes. Furthermore, the bricks used for the construction of the houses were in the fixed ratio of length is to breadth is to thickness. This accuracy in measurement signifies that the people of the Indus Valley civilization had knowledge of mensuration and practical arithmetic. Books of ancient India, such as Sulbha Sutras and Vedas, provide us with numerous pieces of evidence to show that geometry was in practice in ancient India. One of the Vedas describes Sri Yantra, an instrument that consists of 9 interwoven isosceles triangles that are arranged such that they produce 43 subtriangles. Have you ever seen Vedic altars? Observe that these altars are of different geometrical shapes, such as squares, circles, rectangles, triangles, and trapeziums. In the Sulbha Sutras, several instructions are given for people to create perfect geometrical altars. Therefore, geometry was known to Vedic India. It is thus apparent that Egypt, Mesopotamia, and India were the hub of practical applications of geometry. Although geometry was being applied practically in various areas since long, no reasoning was established behind certain geometrical rules. Let's explore and learn about the scholars who set reasoning and paved the way to make geometry a systematic science. It was Greece where geometry was born as a systematic science. The Greeks were more interested in establishing reason behind the already laid statements in the previous civilizations. The Greek mathematician Thales was credited for giving the first known proof for the statement that the circle is bisected into equal parts by its diameter. One of the famous disciples of Thales was Pythagoras. He put forth many geometric properties and contributed to a great extent in the development of geometry. Noteworthy contributions were made by another Greek mathematician, Euclid. He observed that the knowledge of geometry was passed on from one generation to another, either orally or through palm leaf messages. Euclid thus collected all known information and added his own original work, and 465 propositions into 13 books called Elements. Let's explore Euclid's definitions listed in Book 1 of the Elements. We know that point, line, and plane are three terms that do not require any further definition in geometry. Let's see how Euclid defined these terms. Practically, you draw a point by making a dot on a piece of paper, and that this point cannot be separated into parts. The above observation can be put into a single statement, as a point is that which has no part. This is Euclid's definition for a point. Now, make multiple dots aligned in a straight manner as shown here. If you join these points, you get a straight line. Observe that these points are evenly distributed on this line. The above observation can be stated as, a straight line is a line which lies evenly with the points on itself. It is the definition of straight line given by Euclid. Observe this line. You can see that it has a length, but it doesn't have breadth. Therefore, we can say that a line is breadth less length. This is the definition of line given by Euclid. Look at the face of the cube. It has only length and breadth. Such faces are called surface. Hence, one can define surface as that which has only length and breadth. This definition of surface was given by Euclid. However, Euclid defined a plane surface as a surface that lies evenly with the straight lines on itself. Do you know that these definitions given by Euclid are not perfect? Well, if you mull over these definitions, you will notice that the terms such as part, breadth, length, and evenly are ambiguous and need to be redefined. Now, observe the definition of a point. In this definition, a word part has to be specified. Let's define the word part. A part is that which occupies an area. Now, the word area needs to be defined. Therefore, we can see that we will need to define a chain of words to obtain the definition of one ambiguous word. Hence, geometric terms such as a point, a line, and a surface are undefined in geometry. Euclid also defined a few axioms. Let's learn about them. Euclid assumed certain properties to be universal truths that cannot be proved. These universal truths are divided as postulates and axioms. Euclid defined axioms as the universal truths used throughout mathematics. However, postulates are defined to be the universal truths that are confined only to geometry. Let's explore Euclid's axioms. Observe this balance. On its right and left arms are placed two types of stones. stone A and stone B respectively. Observe that the weights of both the stones are the same. Now, let's replace stone B with another stone C. Look, the weight of stone C is also equal to the weight of stone A. We can thus infer that both the stones, stone B and stone C, are equal in weight to that of the stone A. Therefore, if we place stone B and stone C on each side of the balance, their weights are equal to each other too. Hence, it can be concluded that things that are equal to the same thing are equal to one another. This is Euclid's first axiom. To elaborate, if a variable q is equal to the variable p, and if variable r is equal to variable p, then variable q is equal to variable r. If the area of a circle equals the area of a triangle, and the area of the triangle is equal to the area of a square, then can we say that the area of the circle is also equal to the area of the square? By Euclid's first axiom, we can say that if the area of a circle equals the area of a triangle, and the area of the triangle is equal to the area of a square, then the area of the circle is also equal to the area of the square. Observe that on the left beam balance, the weight of stone A equals the weight of stone B, while the beam balance on the right side has equal weight of stone C and stone D. Now, let's add the weight of stone C to the weight of stone A, and add the weight of stone D to the weight of stone B. Observe that the total weight of stone A and stone C is equal to the total weight of stone B and stone D. Therefore, it can be concluded that if equals are added to equals, the wholes are equal. This is Euclid's second axiom. Now, the same holds true if we take out the equal weights from both sides. Therefore, it can be stated that if equals are subtracted from equals, the remainders are equal. This is Euclid's third axiom. Observe that these two circles completely coincide or overlap each other. Therefore, they are equal. Hence, it can be concluded that things that coincide with one another are equal to one another. This is Euclid's fourth axiom. Can we say that the sum of the lengths of PR and RQ is equal to PQ? It is true that the sum of PR and RQ is equal to PQ because, according to Euclid's fourth axiom, the length of PQ coincides with the sum of the lengths PR and RQ. Here's a chocolate bar with 6 pieces. Let's keep it at one arm of the balance. Now, let's place 2 pieces of the identical chocolate bar on the other arm of the balance. Observe that the whole chocolate bar is heavier than its part. Hence, it can be concluded that the whole is greater than the part. This is Euclid's fifth axiom. To understand this axiom, let's consider a variable p such that p is equal to the sum of the variables q and r. Then, both variables q and r are less than p. What can you say about the areas of triangle PQR and triangle PST? can say that the area of triangle PQR is greater than the area of the triangle PST because triangle PST is a part of the whole triangle PQR. Consider these two pairs of identical semicircles. Observe that these two pairs of semicircles combine to form two identical circles. It can be concluded that the things that are double of same things are equal to one another. This is Euclid's sixth axiom. To elaborate, if A is equal to twice of B and C is also equal to twice of B, then A is equal to C. Similarly, the Euclid's seventh axiom states that things that are halves of same things are equal to one another. This axiom can be elaborated as follows. If A is equal to half of B and C is also equal to half of B, then A is equal to C. Let's consider 2 points A and B. Now try to draw more than one line passing through these 2 points. Look, from either points A and B, multiple lines can originate, but there exists only one line that joins the 2 points. From this observation, it can be concluded that from given 2 distinct points, there exists a unique if it is impossible to deduce a statement from these axioms that contradicts any axiom or statement already proved.